doing the opportunities to think about it. So this talk is based on a joint work with Søren Eilers. So it's still, some of the work is still ongoing, so we are still working on it. Before giving a plan for the talk, I will first define what I mean by quantum Lie space. So quantum Lie spaces are defined from one so it's a very well-known and very well-studied example of the quantum sphere. And in this case, in this talk, we will mostly be looking at the lowest dimension. You can define Lie spaces and those spheres for all dimensions. But since I will only work with the lowest dimension, I will give you the definition. So yeah, we will look at a quantum version of this classical Q sphere. And it's defined like this. So you take this parameter Q between 0 and 1. So you want to define your sphere. And then we still write this C of SQ3. It's not a commutative system algebra. Now it's a non-commutative universal system algebra generated by two elements, and then it has to satisfy these relations. So you see that now this Q shows up. So we get something which is non-commutative. And we still have that the sphere relation is satisfied, which justified that I want to call it a quantum sphere. So if you let Q be 1 in these relations here, you see that then everything moves. And we get precisely that C of S13 is just a commutative system algebra of continuous function on the classical sphere, which also justifies this notation here. So we think about this SQ3 as the virtual space, as a virtual non-existent space, which we call a quantum sphere. Okay, just a quick remark where these relations actually come from. So we know classically that S3 is homomorphic to SQ2. So here in the quantum version, we also get that this SQ3 is actually the same as Voronovich's SQ2 group. So those of you who were there last week, we saw that Christian talked a bit about this SQ2 group. And in general, if you want to define those for higher dimension, it's still giving like it. So this is still a subalgebra of this quantum group here. And by this I mean that it's actually something called a quantum homogeneous space. But for now, I will just work with this SQ3. We also have a natural circle action on this quantum sphere. It just comes from the universal condition here. If you plug into this WZI in the relations, you see that they are still satisfied, so we get a star homomorphism like this. And the reason why I'm pointing this out is because I want to look at equivariant isomorphism. So isomorphism which preserves this circle action. Okay, so now we can move on to Lie spaces. So let me just recall the classical construction, and then we will see that we can actually we will just copy that construction and define the quantum. So classically we take a parameter R, and we also have this M underlined here, which consists of two positive numbers. I will refer to this as the weights. And here classically we will have to assume that the greatest common divisor here is 1. Otherwise the action will not be great. And then we define Lie spaces as this quotient space here under the action of this finite cyclic group of order R. And it acts like this. So you just take your generator of the group, and then you take the power of Mi or M2. And now we can just copy it to this case. So again, we just define an action on C of SQ3. Like this. It's the same as I have above. And then we let this C of LQ3, R and M, be the fixed point algebra under that action. So the Lie space is just defined as fixed point algebras under this action here of this quantum sphere. And then again, we think about this space here as a virtual space known as the quantum lens space. And just a remark here, we can also look at cases where the grid is commutative is not. Yeah. And of course, since this is a subalgebra of SQ3, we also have a circle action inherited from that. And this is the circle action I will talk about when I want to consider equivariant isomorphism. Okay, so let me, before going more into these equivariant isomorphism, let me give you an idea of what is known about these quantum lens spaces, or at least what I'm aware of that we know about them. So first of all, we know that they are graph system algebras. So Ralph talked about these group graphs yesterday, and the good thing knowing that they're graph system algebras is that we can decide if it's simple, we can describe the ideal structure, we can compute K-theory and K-homology. So we know a lot of things about them. And first of all, this was done by John here and Wojciech. In the case where this greatest common divisor is 1, and then later on it was extended. Okay, and a lot of very nice things about knowing that they are graph system algebras is because we can actually classify them. So there is this classification result by Isomorphism, Lewis and Sørensen, where they gave a complete invariant for unital graph system algebras. A graph system algebra is unital if you have finite many exists. And here they use the variant is something called the reduced filter with K-theory. I will not go into that, but it means that you have to look at ideals and quotients and K-theory of them, and also maps between them. But it's very nice that you can actually classify them using this description. And for lens spaces, it actually becomes even better, because this classification source boils down to just some matrix algebras. So when you have a graph, you have the adjacency matrix, which means that you just plug into the matrix the number of edges between the vertices, and then you can do some calculations with that, and then you can classify them. So it's a very nice result. And using this classification result, they looked at the case where the greatest common divisor is 1. And here they found out that in dimension 3 and 5, so lens space is defined by quantum spheres dimension 3 and 5, that here they are just all isomorphic. And in dimension 7, you get either 1 or 2 isomorphism classes. So it depends on if 3 divides R, the order of Decken group or not.
Yes, it's also equivariant.
No, this is just isomorphism. Okay. Yeah, I'm not going into the equivariant. This classification result is only for isomorphism. And then under the assumption that the greatest common divisor is allowed to be not to be 1 for precisely one of the weights. Yes.
I mean, in the case if Q is 1, then you get an ordinary lens space. And I mean, these are not all isomorphic.
You cannot use it for you can so.
Is Q not different from 1?
So we don't look at Q being 1. It's only for Q, not 1.
So the once is not 1, then somehow you have more really different user topology.
Yes.
Classification is quite different in quantum case compared to classical case. Very different.
So we're not. Also, if you look at I try to compare the classification of the classical and the non-commutative ones, and they are different. You can see that there's something that is isomorphic and it's not isomorphic or the other way around. So yeah, and then as I said, in a collaboration with Thomas Gottfried, we extended this result to the case where the greatest common divisor is allowed not to be 1. So this is where we're using this machinery of being a graph system algebra. Then there's also been some work on these quantum lens spaces from a more geometric point of view. I will just mention it. But by realizing them as these line bundles here, where you look at quantum lens spaces as a total space bundles, and then you have the base space, something called quantum weighted predictive spaces. And then there has been some work by several researchers on constructing a non-commuted version of the sequence. And from that, calculating K-theory and K-homology and giving some explicit representations for K-theory. And there's also been a bit of work on spectrum shapes. And everything here is under some conditions on the weight of the lens spaces. But just to say that there is also more geometric window. But yeah, in this talk, we will just look at them as graphs. Okay, so this is the question I want to ask. So if we have two isomorphic quantum lens spaces, so we know that R here has to be the same for them to be isomorphic. But we can take different set of ways. And if we assume that they are isomorphic, under which conditions do we then have that they are isomorphic in a way that preserves this action here, the circle action. So it means when we have an isomorphism such that it intertwines this action. And we can also ask about the stabilized version, where we now look at this action. And the reason why I'm saying this is because we actually have to go through this to end up having a result. Okay, so now the plan for the talk. So first of all, we need to look at quantum lens spaces as graph diagrams. So I will give you the description, but just for the smallest dimension in some examples. So,
so what is the assumption on Q exactly? Is it like a
Q? What is Q? Q is just a parameter between 0 and 1.
Between 0 and 1. Can it be a root of unity? Not 1.
No. Just no.
Not even a root of unity.
Positive.
Yeah, it's
What?
It's positive.
Between 0 and 1.
Zero is excluded.
Oh. Okay.
Okay. Q between 0 and 1.
All right.
And then I will give a complete description of this equivariant isomorphism of quantum lens spaces of dimension 3. I already said to you that they are all isomorphic in dimension 3, so we cannot distinguish them there. But it turns out that actually we cannot find quantum lens spaces. They're not all equivariant isomorphic. So we actually see some different things here. And then I will give you some idea of, and this is still ongoing work, what we have to do for higher dimension. What we're doing here is, it works for dimension 3. We don't have a tool like I described in the beginning, where you have this classification result for determinant isomorphism. So we need to come up with some ideas and try some things out. So this is some ideas to how to actually generalize. So since everything will be about graphs to start with, let me briefly give you the definition. You don't have to remember it if you have not seen it before. But what we are working with is direct graph. It has, this is E0 is the set of vertices, E1 is the set of edges, and then you have the range and source map telling you where the edge ends and where it starts. And we can have loops and everything is allowed. And then we construct this universal cis-diagram generated by here a set of connections, and they are indexed by the vertices in the graph. And then we have a set of partial isometries indexed by the edges in the graph. And then they have to satisfy some relations. And the relations captures the structure of the graph. So I will go through them, but we can also give us some examples here, which I think are very important. So first of all, they have to be orthogonal. You don't have this condition here. If you have different, if B and F are different, then this side is F, has also to be 0. And then we have the last three, which are the known as the conspicuous relations. So this projection here get out of the partial isometries has to be the same as the projection corresponding to the range of that vertex. And the other round, we have that this is a subprojection of the projection corresponding to the source of view. So now the last one here, if you take the sum of all of these, which start in V, then you get And this is only true if this set here is finite and non-empty. So we don't want to have an infinite sum, or it should not be empty. So, yeah, and then you see here you have, this is just to give you some examples, of some, but there's a lot of them. And then we have, very important here, we have this gauge action. So we have an actual circle action on the vertices algebras, and it just fixes the projection corresponding to vertices. And the partial isometries here you have to multiply by the element in the circle. And again, you see that if you look at this side here, then it satisfies the same relation, so we get a star. So the most important thing to remember here is this gauge action, which I will come back to. Okay, so now Jankian and Richik, they proved that the Wagner and Zuckerman quantum sphere are actually and this construction here actually goes through an explicit isomorphism. It's quite complicated, but it's and here they showed, so this is just for Q3 and Q5, and then it continues like that. I think you see the system. And also note here that the graphs algebras, they're independent of the parameter Q, so you actually get that they are these are all isomorphic for any Q between 0 and also including 0 and not 1. So it also shows you that they actually also the graph. Let's see the picture. Okay, so now that's why it's important that this is actually an explicit isomorphism. Under this isomorphism here, this action here, if you go back to the beginning, this action here defining the lens spaces becomes the action I have written here. So we have this rho underline MR, and it just fixes the predictions. And then you have to multiply here by this generator of the group, the power mi. So the m here depends on the first edge. Maybe I should say that eij here, I mean, so this is v1, v2, then this is v1, 2, v1, 1. So then we know that our lens space is isomorphic to the algebra of the graph system algebra under this action here. And then there is this result by Plus, which says that this fixed point algebra here can be described as the corner of another graph system. I will describe this using an example, but this comes from a more general construction of a screw product graph, where you have a labeling of the graph, so meaning a map from the graph to the group, and that's why I have this in the input here. And then it was shown that this corner is actually itself a graph system. So this is how you can show that they are actually graph systems. Okay. Yeah. So let me describe this graph for you with an example. So our focus is again on the lowest dimension. So let us just look at that example. And we are assuming that the greatest common divisor is 1. So here I let R be 5 and M be 1, 2. And then this graph here is constructed in the way that you have 2 levels. So you take your vertex here, this is the tree you're looking at, so you have V1, V2, and then you make 5 copies. And then the edges are determined by the weights. So here we have to add M1, which is 1. And since we are calculating everything modulo 5, go back. Going from this level to this level also depends on the first parameter. And then on the second level, you have to add 3 every time, and then you go. Yeah. So it has in general 2 levels. The one here for lowest dimension, R vertices at each level, and then you have precisely one edge going from Vik to Vjk plus Mi, and everything calculated. If you let the dimension be bigger, you get more levels, and you get edges between each level in this direction here. So you see already that it becomes much more complicated looking at higher dimensions. Then this graph here, which I said before is the graph's algebraic description of the Lens spaces. You get from taking the corner of the graph's algebra here by these two vertices. And the way you construct it is just that you take these two predictions, which are in the corner, you put them here, and then you have to count some specific paths between them. And these paths are called invisible paths. And it means that you the number of edges here will be the number of paths from V10 to itself, not going through it. That's why you get one. Same here. Get one of them. And the next one is the number of paths from V10 to V20, and here you will get 5 of them if you count them. Because again, you're not allowed to go through those vertices. So in general, you actually would get R paths here. So it's easy in the lowest dimension. But again, I think you can imagine if you have more levels, then it becomes quite complicated to count those paths. And that's what you have to do with these with classification results I talked about in the beginning. Classifying isomorphic lens spaces, you have to come up with the adjacency matrix, so you have to count all these paths, which makes the computation
So M isn't used here, right? So it's just the R equals 5 that appears in this new graph.
Yeah, exactly. So it does not depend on M actually. Yeah, precisely, because you just get, it doesn't matter, you come back here. Okay, but remember that I have assumed here that the greatest common divisor has to be 1. Actually, in the lowest dimension, it's the same result we get, but for higher dimension, things become much more complicated because then you could have 2 non-connected cycles in the levels. Yeah. Okay, so now we see that if we fix R, then this graph here is just the same for any choice of M, which is precisely gives us the result that the quantum lens spaces of the lowest dimension, they are just all small. But you also see that going from this to this picture, we have a problem with this action. It disappears. We don't see. We don't keep the structure of the action when we pass it. Yeah.
Maybe this is a silly question, but when you were like describing this procedure of getting a C-star algebra from one of these graphs, I felt like there was something in there about like there are specific partial isometries that are generated by these arrows. Like, does this picture imply automatically like what those have to be, or is there extra information somehow about?
Do you mean if you have the graph, then you know precisely the relations between the partial isometries? Yeah.
Okay.
Yes, you have the graph, then you have all the information you need.
Okay. Cool. Thank you.
That's the nice thing about the graph system. Just look at the graph and then you have the information. Okay, so now let me come back to this equivariant isomorphism in lowest dimension. So just to recall for you, we have this action of the circle of the sphere, which gives us an action of the lens space. And now are they isomorphic in a way that preserves this? That's the question. And what I just have explained you, we have gone through several isomorphisms. So let me just give you an overview here. First of all, we have that these lens spaces, they are isomorphic to the fixed point algebra, this action here. Then the action of the circle is just under the isomorphism gives you the gauge action on the graph. Okay. Now if you go to the corner, this action still gives you the gauge action on the graph here. But when you have to go to this graph system algebraic description, which was the last graph we said, it is no longer the gauge action. So the action here is not preserved. And it has something to do with that you look at paths in your graph and then you map them to an edge in another graph. So you see that this action breaks down. So we have to stop here. So with the classification of the isomorphism, we could actually go to this picture, but now we have to stop at this corner. And in fact, it actually turns out that we cannot just find another graph where this is preserved. So there's a problem saying that this cannot be equivariant isomorphic to any graph system. So we have to look at it. And there's no known results we can use. So I will give you an idea of what we did. And what I will start with is one side of the story. So first of all, we looked at just naively at the graph system algebra and try to construct the isomorphism explicitly. And then we got a condition, and then we would like to also get that this is an infinite game. So if we look at the graph over here, giving you the here, then we want to look at some specific paths in the graph. And here I just have E11C, it means that we will do this here, and we do this times. And we want to look at the numbers, and they will be important. That's why we want to start this direction here. So these numbers has to satisfy this condition. And it just comes from the fact that if you take your action, remember this is the circle action on the graph, and you take this partial isometry corresponding to that path. By that I just mean that you take the partial isometries corresponding to here, t times here. Then you say that if you get, then you have taken to the power of this. But if this is congruent to 0 mono r, you get precisely that this element here is inside. That's why I want to look at precisely those numbers here, because then it gives you partial isometries corresponding to paths, which actually lies in this one. Yeah, and the action here is just given by the length of the path, so it's t plus s plus 1. Yeah, not something complicated, but those numbers will show up. Okay. Yeah, so this is just from before. Now, if we look at an example, just the one from before here, and now we have n equals 3. And then we look at these numbers, because if you have, if you look at all these s alpha ts, then you can show that they generate the graphs, generate this fixed point algebra of the graph system algebra describing the lens spaces. So if you can find a way to map them to each other in a way that preserves the action, then we would have an equivariant isomorphism. So these numbers becomes important, because if you can look at these sets of numbers here, and you can then you can see here that you could just map the generator corresponding to this one here to the one here, and this one to here, and this one here. Okay. But now we also need to take into account that we can calculate everything modulo r. So that's what the colors indicates, that 7 and 2, they're congruent modulo 5, and 3 and 8. So the map, to describe the map, I have to look at the graph here for the quantum sphere in 2 different notations. So here I just use alpha, and here I use beta. And then the map is, as you would expect, we still have the same beta action, the map is same here. This alpha 0,3 gives you this number here, it's t plus s plus 1. And then you map it to the one corresponding to this one here, which is beta 1, 2. For the ones in where they are congruent modulo 5, you have to multiply by the adjoint of SH225, meaning that you subtract it. And you can do that because this operator has normal, which is also very important. You do the similar trick here and here. So this is our, this was our first starting point, and then that's why we want to do these numbers. Okay, so it means just from what I said, in general we can construct an equivariant isomorphism if this set of numbers here will be the same for two set of weights, just as we saw before. This, yeah, it does not look that nice, but we can show that this is the same as the set of numbers when we multiply this greatest common divisor for 1 minus, and here I mean the multiplicative inverse of M2 and Mi with R. And then you go with velocity. Yeah. It's not a difficult calculation, but it's much nicer to do that because it means that if those two greatest common divisors are the same, then they are equivariant isomorphic. So it's very easy to check if this is the case. Yeah. So I hope you have an idea of why these numbers are important, and that's why this maybe it looks a bit out of nowhere, this condition, but it has something to do with these numbers. So now the question is, we go the other way around, which is a bit more difficult. So the idea here is to show that the ideal structure of the fixed point algebras under gamma, so the fixed point algebra, this one, they cannot be the same if those numbers are not the same. So if this is true, then of course the fixed point algebra of this one under the action has to be the same. And then we will show that the ideal structure cannot be the same if the numbers are not the same, which will give us the other equation.
We only talk about the subgroup generated by this number, right? So if they generate the same subgroup, they have also the same weights. If they differ by a unit modulo R,
yeah,
would this be enough? Or
so
you said that the important set is all the multiples of them. And so if they differ by a unit, modulo R, they should have the same multiple.
You can, you can of course move everything by R all the time, if that's what you mean. So you can, you have to calculate everything modulo R, so it has.
Let's say if R is a prime, then if I take any element and look at its multiples, unless I take 0, its multiples.
Okay, yeah, but you also get that if it's prime, then you either get all the numbers or you just get 0.
Yes, exactly.
Yeah, but it's also everything is a lot easier when you have a prime number. Yes.
Mm-hmm. So my comment was that these sets could be the same without the generators, these GCDs being the same. If you have, if R is a prime, then I think these are always the same set, right? Or unless it's just
yeah, but either you would have 0. Yeah, it's either 0 or R.
Mm-hmm.
So that's the only two opportunities. Yes. Yeah.
Okay. Well, let's just go on.
Okay, but that's precisely correct. That if you have a prime number, then you only have two different cases. Okay, perfect. I will show you some graphs in a moment, and then you can see some calculations here and see the difference. As I said, we want to look at the fixed point algebra of this graph under this action here, and see that they cannot be the same. So for that, we can use another solve of this, which gives you a description of a fixed point algebra as the corner of another graph algebra. So this is just an example. So if you have a graph like this, then you construct this screw product graph here, and now we just have another labeling, which means that you have to, you put your vertices like this, and then the edges comes from adding 1, so you shift by 1 in time. So that's why you get, something like that. So the loop will just become like this, and so on. And it means that you always make those loops disappear, which means that you have an AF algebra. It's an AF algebra if and only if you have no loops. So, and then this fixed point algebra here is isomorphic to the corner of this graph system algebra, which I gave an example of here. And the projection here is just the one taking the sum of the projection here at time 0. Okay, so we will use that result because it describes this fixed point algebra. And now there will come a lot of graphs and a lot of corners, and I have tried to indicate it with colors so that you can follow it. But now we know that this length space here is isomorphic to the corner of this graph system, but this was just the source in the beginning. So I'm just recalling the example from before. And now I'm indicating the connections. We take the corner right with green. Okay. So now the fixed point algebra of this one, not the corner, but just graph here, is by this resource tutor before. Yeah, the corner for some other projection, and then you have to take the screw product at the set. So you first have a graph where you take this screw product with some labeling, and then you take it again with modeling. Okay, and then you take the corner by the sum of these predictions. Let me give you an example. So yeah, this is also why I didn't want to. So you take this graph. This here is the first level. You put it here, and put the second level here. Okay, so this is the graph we had before, and then everything is shifted like this on the board. Okay. Yeah, and then you have to take the corner by the orange edges here. Yeah. Big graph. But now we can show. Now it can be shown that this fixed point algebra here is then isomorphic to the corner for another prediction of this. This graph again taking the screw product 2 times with different labels. So we don't want all of it. We only want to look at the ones where the corner is taken for this prediction and this prediction, coming from the fact that we're only looking at those two. We have to show. So now we look at the corner of this big graph for these two vertices. Okay, and now it looks a bit more nice. So now you can. So now we remove everything which is not connected to those two. So, and yeah, show that they continue here to infinity. But now since you're only looking at what comes after those two, you can remove everything here, and you can remove a lot of vertices and a lot of edges. So we end up having a graph. Okay, and I will refer to this graph as FRN. And then we will use the fact that the fixed point algebra of this graph here describing the quantum field is multi-equivalent to this system. And from the fact that you have to. Okay, so here's some examples. So if we do it for different weights, then you see here that for 1 and 3, 2 and 3, we get the same. It's not the same graph, but the ideal structure are the same. You have the same number of lines in the second level, which corresponds to minimal ideals in the graph. But here, and this is precisely the example I showed you, where we can construct an explicit isomorphism, equivariant isomorphism. But if we take 2, 2, then we only have 1. Yeah. And those two are the only. You either have all of them or one of them. Because you have a only 2 examples. So the ideal structure tells you that those two graphs are what they can be in a way that, yeah, they cannot be isomorphic, and then we have to go back. But the result we have here is that the number of minimal ideals equals this number here. And now you see that this greatest common divisor actually shows up again. So you can, by looking at this fixed point algebra and counting minimal ideals, we actually see precisely the number which we saw when we constructed the equivariant. And here's just an example. Now we have something which is not prime, and then we can have those 3 different equations, either 1, 2, or 4. Okay, so now let me go back again. So if we assume that those numbers are not the same, then these algebras cannot be the same, because that ideal structure will not be the same. And then we know that this graph, remember, it is multi-equivalent to yeah, this one and then we can go through the stabilization with the compact operators, and then we end up having that they cannot be equivalent. We actually pass through the because of multi-equivalent, we pass through the stabilized. Okay. So this is our result, and I almost explained everything. So they are equivariant isomorphic, even though this stable equivariant isomorphic. And then it's equivalent to those pieces of the same, but much easier. It's much easier to do that with number. Yeah, and then we also wanted to count the number of isomorphism classes. So if R is even, then the number of even number of isomorphism classes equals the number of even divisors, and if it's odd, then it equals the number of divisors of R. Again, you see if it's prime, then it's just 1 and R. And this was actually not that trivial. Okay, so as you see, everything here works for dimension 3, and it's very important that it's actually dimension 3. So if you want to count to dimension 5, then you can try to do the same trick constructing these equivariant isomorphisms by looking at generators. It becomes again a bit more complicated due to how the graph looks like, but it is possible to come up with a condition. But the condition is that we have 3 different set of numbers, and they have to be the same. So it's not as nice as we have for dimension 3. And then it turns out that if we want to try to do the same thing, looking at the ideal structure of that fixed-point algebra, then we have examples where the ideal structure of fixed-point algebras, they are the same, but I cannot construct an equivariant isomorphism in the way I want. So we cannot use the same trick as we use for dimension 3 to actually distinguish them. If it is indeed correct that maybe you can construct it in another way. But that's why we need another tool for that. And yeah, for that I want to explain something called the dimension triple. So if you have graph E with finite many vertices, then you can define this dimension triple. So it consists of the K-theory of, again, this is just what I have got, the K-theory of this periodic graph, and also with the order, and then we have this shift map, just as you could, just a natural right shift, shifting everything right there. Okay. Then there's this conjecture by Ehlers and Ruiz that if you take this graph and you say that those two should be equivariant isomorphic, then they should be equivalent to having isomorphic dimension triples, and then you have to add also that the class of this mechanism to the class of this one. This is just corresponding to taking the sum in time 0. Okay, so it is known for some examples. The evidence for this to be true for all graph-system algebras are still very small, but it's known to be true for all simple concrete algebras, meaning finite graphs, no sinks and sources. It's also known by the result by Edgren and Ehlers that it's true for all graph-system algebras, which are AF algebras, and then it's known to be true by all of them for something called amplified graphs. So it means that if you have an edge, you should have infinitely many nodes. Every time you have one, you have two. But there are no known counterexamples. So I talked with Søren about it, and he has been trying to construct something, and he has also tried to extend this, to prove this for more graphs, but he hasn't found any convex yet. Then we can give maybe even smaller evidence that this could be true, but I will say it anyway. If we now take the version here, where we put a corner instead of the graphs, and then we have to take this sort. It's okay to kind of track it. But you have to change this not to take all of the prediction at time 0, but only some of them. Okay. Then we are asking, do we have that if they are isomorphic, do we then have that these dimension triple with this number here are the same? And maybe I should say now that by an isomorphism here, I mean a positive map, which intertwines this shift action, and it has to send this prediction to this prediction. But in our case, if you look at dimension 3, this the first one here is just set to the power of 2r. So describing this isomorphism can be done by using a matrix, and then you set up some condition for that matrix by requiring the shift to be preserved, and that prediction here to be sent to the other prediction. So in dimension 3, it's actually not that difficult to compute. And again, we see precisely this number showing up. So if we try to figure out when do we have a solution, precisely when this thing. So it's not needed for dimension 3 because we can distinguish them by the ideal structure of that fixed point algebra, but we try to do it because then we can actually see that this holds for these quantum length spaces of dimension 3. So here it is true that they are equivariant isomorphic, if and only if this dimension triple with this prediction here, they are safe, and if and only if this number here is the same. So it gives us a way to try, a method to try on higher dimensions. And here we have some results which we are still working on it. But if we just look at a prime number, we take 2 set of weights, and now again in dimension 5, so we have 3 weights. Then the following are equivalent, so these 2 are equivariant isomorphic. Our conjecture is that it's equivalent, that these 2 are equivariant isomorphic, if and only if it satisfies one of these conditions. So either you have that all of the weights are different, so you have a large group, you just have to require that they're different. Otherwise, you have to obtain them from n just by multiplying by a constant on each. And Søren, he did some calculations of this in just using Mabel, and so we have a lot of data we can try to look at, and that's why we come up with this conjecture. And right now we have proven that 2 implies 1. If this is true, then you can construct equivariant isomorphism in a similar way as you did for dimension 3. It requires a bit more work, but it's possible. And then, as I said, we have some experiments in Mabel, which indicates that 1 implies 2 is also true. But if you go to something which is not a prime number, it's not that easy to see the system. So this is why we are still working on it. We are trying to see if we can use that approach and see if we can come up with the same condition here for when you have a solution to that matrix. Okay. Yeah, actually, I think that was